and today we're going to talk about nuclear reactions. In particular, we're going to first talk about radioactive decay, and then we'll talk about other nuclear reactions, principally fission and fusion. Okay? And I have all of this in a PowerPoint document, which I'm going to share with you in 1 second, so hang on. Very good. So our subjects for today are radioactive decay and nuclear reactions. Okay? And we'll start by talking about radioactive decay. And we'll see that there are three principal types, what's called alpha decay, beta decay, and gamma decay. And these names, of course, we'll see what they mean in a moment. But you can tell alpha, beta, gamma that they were they were thought up back when people knew that there were three different processes going on, but they had no idea what was involved. Of course, now we know exactly what's going on. Let's take a look and find out. So to begin with, remember that elements come in different isotopes. And different isotopes of a particular element, let's say silicon here, all have the same number of protons, but they have differing number of neutrons, okay? And thus a differing atomic mass. Some of the isotopes of silicon are stable, but all of the others are unstable. A few have relatively long half-lives, and the rest have very short half-lives. They're shown in white here. And the same is true of all of the elements. Okay? So what about the decay of radioactive nuclei? How does that occur? So there are three principal radioactive decay processes, and they're shown here: alpha emission, beta emission, and gamma emission. In alpha emission, the nucleus decays by emitting an alpha particle, which we know is just a helium-4 nucleus, a particularly stable group of nucleons. In beta emission, the nucleus emits an electron, or sometimes an anti-electron. Okay? But keep in mind, this is an electron that's created inside the nucleus as a result of a reaction. Typically, when a neutron is annihilated, leaving behind a proton, an electron, and a neutrino. It's not one of the outer electrons in the atom that were already present. And finally, there's gamma emission, where a nucleus in an excited state drops down to a lower energy state and emits a gamma ray. Okay? All of these processes start with an unstable nucleus of one kind or another, and they're all spontaneous processes. They happen all by themselves, and they're all quantum mechanical processes, so they're unpredictable, just like all quantum processes, all individual quantum events are. Here, let's start with alpha decay. So in alpha decay, a nucleus, typically a heavy nucleus, decays to a lighter nucleus with the emission of an alpha particle. We can sketch the reaction out here. The initial nucleus, we'll call it XAZ, decays by emitting a helium-4 nucleus. And then just conservation rules tell us that when that happens, the mass number has to decrease by 4, obviously, and the atomic number has to decrease by 2. Now that tells us what the product nucleus will be. So, for example, one alpha decay reaction is the decay of uranium-238 to thorium-234 plus a helium nucleus. Okay? We can figure out easily how much energy is produced or released in a particular reaction. It's simply given by this formula. The energy released, we'll call it Q, is just equal to the mass difference times c squared. And in this mass difference formula, one thing to keep in mind, we're going to use the masses of the neutral atoms, since those can be measured very accurately. So this is the mass of the parent nucleus, the mass of the the mass of the parent atom, the daughter atom, and the helium-4 atom here. Since no electrons are emitted or or destroyed in this reaction, um, it's fine to use the masses with the electrons included, since electrons are conserved. Okay, so this is very straightforward. Okay, in fact, we can predict whether a nucleus will be unstable with respect to alpha emission simply by running this calculation to see if Q is positive or negative. If Q is positive, then the system can lower its energy by going through alpha decay, and eventually it will. Here, just as an example, why don't you try this? Find the energy released in the reaction we just described, okay? The decay of uranium-238. So here's some data that you'll need in order to do that, and then there'll be a reading question about this in 1 second. Very good. Here, let's go on. Something interesting about alpha decay. Alpha decay can be described through a tunneling model, okay? And the idea is that in this model, the alpha particle is thought to exist within the nucleus, and then it escapes by tunneling through the potential energy barrier. So the alpha particle is a particularly stable and strongly bound arrangement of nucleons. We might think that within the nucleus that this alpha particle already exists. It's sort of a clump of nucleons that maybe orbits the rest of the nucleus in some way. In any event, this nucleus has some kinetic energy, and you can imagine the potential energy that it faces. So there's a strong attractive force that keeps it within the nucleus. That's the strong nuclear force. But the strong nuclear force is very short range. So if the alpha particle could be taken even a little bit outside of the nucleus, then it would see a strong repulsive force due to the Coulomb interaction, okay, the repulsion of the protons in the alpha particle and in the remainder of the nucleus, okay? And so the potential energy outside is a function that's falling with increasing distance. So we end up with a barrier like this, and so it's possible that the alpha particle can tunnel through the barrier, okay? What determines this? Since the barrier is fixed, it's just the energy of the alpha particle, okay? And we can actually measure the energy that the alpha particle had inside the nucleus just by measuring the energy of the alpha particle that's emitted in the reaction. This is an example problem in the book, but it's not one that we're going to go through. But the result is that the transmission probability is proportional to e to the minus a, the mass number, divided by the square root of the energy, okay? And here's some data about this. So here are data for the alpha decay of isotopes of radium. So they all have the same number of protons in the nucleus, but different isotopes have different mass numbers, okay? On the y-axis, we have the log of the half-life, and on the x-axis, we have the energy of the emitted particle in MeV. And the red line is the prediction of the tunneling model. So as the energy increases, the half-life decreases very rapidly. So the data for all the isotopes of radium here, the half-lives span 15 orders of magnitude, and yet all the points lie reasonably close to the prediction of the tunneling model. It's kind of amazing. It's one of the strongest pieces of experimental data supporting tunneling, absent things like a scanning tunneling microscope, which is just built on the idea of tunneling. Anyway, it's really interesting.